Okay, so welcome again to this second lecture. Typically, I would like to start with a short summary of what we have done last time, so that everybody's back on track, understanding kind of the status that we have. So last time we have looked at the so-called Couette flow. And Couette flow is the flow between two parallel plates. So in this sketch, we have two parallel plates here. And these two plates, they move in opposite directions of each other with a speed of uw each. And the two plates are separated by a distance of 2h, 2 little h. And then what we did last time was to calculate the solution of the flow using the Navier-Stokes equations. The Navier-Stokes equations are summarized here. And we were introducing a number of common simplifications or approximations, let's say. And these approximations are actually quite important to understand why we can do these in various circumstances, because this will come back when we calculate other exact solutions of fluid dynamics problems. So, for instance, for channel flow or pipe flow, and even more complicated cases. So the common approximations are that we can neglect the time derivative if we consider a steady flow. We can neglect spatial derivatives in directions in which we do not expect any development. So that means we are considering a fully developed flow. In this case, it is in the x direction. However, we cannot directly assume this for the pressure typically, but in this case, in the case of Couette, we can also say that the pressure, there is no change in pressure in the streamwise direction. That's why also dp dx is going to be 0. And then last but not least, we also say that the whole flow is two-dimensional, meaning that both the w component and the span-wise derivatives are 0. If you now put all of these approximations together, we introduce those into the Navier-Stokes equations, and we use the continuity and the momentum equations. We solve them, then we get the well-known result that is written here for Couette flow, namely that v and w are 0, and u, the streamwise velocity, will have a linear dependence on the vertical coordinate. And that's exactly what I have also sketched here in green. This is now the velocity profile that you get for Couette flow. So essentially, it means that essentially you introduce momentum in the flow from the two walls, and then you have the viscosity that kind of redistributes or diffuses this momentum that we introduce towards the center of the channel where kind of the two sides merge. So that's the physical idea behind it. So we get this linear profile, and in the end we can say that this is a flow that is essentially driven by the two walls, by the shear introduced by these two walls, and therefore we call this flow also to be shear driven. Today, later on, we will also see another flow which is pressure driven, which is slightly different. We will talk more about that later. What we then also did last time was to look at the wall shear stress. So essentially, we looked at this position and this position at the walls, and we tried to identify what types of forces are being transferred at these two places from the fluid to the wall. And we realized that this is actually this wall shear stress, so the multiplication of the viscosity times the wall gradient, u dy at the wall. So this is what we call wall shear stress, tau wall. And we then also introduced the Reynolds number, because we realized that maybe looking at non-dimensional problems could be relevant. So we introduced the Reynolds number as the multiplication of a length scale times a velocity scale divided by the viscosity. And in the case of Couette, we get h times uw divided by nu as the Reynolds number. And then the main result would be that we could then write the non-dimensional wall shear stress. Maybe I should write that here. So that's the non-dimensional wall shear stress. So essentially tau w divided by the dynamic pressure that gives this, this CF. And this can be expressed with the Reynolds number as 2 divided by Reynolds, which of course is exactly that type of results that we were looking for, because now we have an easy way of relating the Reynolds number, which is kind of that number that kind of tells you what are the viscous forces in the flow versus inertial forces. So we can relate that number to the friction at the wall. And this was then also the last result that we plotted last week, last time. This famous or this important diagram where we have CF on the y-axis, we have the Reynolds number on the other axis. We do it in a log-log plot, so we have the ln here and the ln here, and then we just plot the wall shear stress or the CF. And then we have seen that, of course, this 2 over Reynolds that we have derived here, that gives a straight line here, which has a slope of -1 because it's 1 over proportional to 1 over Reynolds. But then we also discussed briefly that actually this is not true for all Reynolds numbers. At some point, the flow becomes unstable, becomes transitional, goes from the laminar state into the turbulent state, and then your relation will probably look more something like this, where first you have a jump up, but then you also have a much lower slope of the CF afterwards. And this slope is typically proportional to the Reynolds number up to maybe -1 divided by 5 or so. But this is not an exact result. This is an empirical result based on data. But the important thing is that you realize that the slope in the turbulent region is typically lower than it was in the laminar region. But the important thing now is to understand that at a specific value of the Reynolds number, for instance here, you will get one value of the friction, but typically it is like that for the same value of the Reynolds number, if you now kind of would consider this line to extend, this line to extend, it would essentially mean that at a specific value of the Reynolds number, the friction that you get if you had a laminar flow is lower than if you had a turbulent flow. So this point is lower than this point here. And this, of course, is a general result. Laminar flows, they exhibit lower friction than turbulent flows would do. And of course, that also motivates most of the efforts in flow control when you try to reduce the drag of an object, an airplane, a car or something, by essentially making the flow laminar instead of turbulent. That's exactly what you see. Okay, so this is essentially what we have done last time. Do you have any questions or any comments that we should discuss a little bit more regarding that? Okay, well, then I guess let's continue with the new material for today. As I said, we will spend first a little bit more time on this and Couette flow, but then we look at channel flow, and at the end, we perhaps go further to the vorticity equations. But let's now continue a little bit with kind of this idea of expressing the friction as a function of Reynolds number. And one kind of important or relevant application of that, just make this a little bit bigger, so that we can see it a bit better. So one important application is the so-called Moody diagram, which I guess is an engineering diagram which most of you have already heard about. It was actually developed by Louis Ferry Moody, was a professor at Princeton University for most of his life. He lived in 1880 until 1953, so kind of in the beginning of the 20th century, when kind of fluid dynamics was developed as an important engineering discipline with the start of airplanes and so on. And he developed this Moody diagram in 1944, essentially as a way of summarizing all the experimental data that was available at the time into one diagram. So there was not a lot of physics going into it. it was mainly an exercise of plotting data that was available. Much of the data actually came from Johann Nicorazze from Germany, who did a lot of pipe flow experiments in various conditions during the 1920s or so, together with Ludwig Prandtl in Göttingen. So most of the data in this plot, ironically enough, came actually from the Germans, from Nicorazze at the time. We will talk about Nicorazze and Prandtl also later on a little bit more, and when we understand how much of the fluid dynamics, the early fluid dynamics was actually coming from the lab of Ludwig Prandtl. Anyway, let's now look a little bit more in detail on what this Moody diagram actually is to understand how it relates to the work that we have now already looked at. So first of all, let's look at the axis. So down here, we have the Reynolds number. I need to say that this actually is about pipe flow, but it doesn't matter. It has the same features as couette flow. Anyway, you can define a Reynolds number in a pipe. You would define it kind of with the diameter of the pipe. You have V as the velocity or the bulk velocity, and then you have the viscosity. So a similar definition as we have. On this axis, we have the friction factor. The friction factor, again, you can define in various ways. It's essentially a non-dimensional wall shear stress, but which is very similar to the CF that we have introduced here. And what does it show? Well, it shows essentially for low Reynolds number that there is this linear decay of the friction factor as function of the Reynolds number. Here for pipe flow, it is 64 divided by Reynolds. Also, this is a result that we will derive later in the course. But of course, this is exactly the same, the same in spirit as we had derived for couette. So we have something that is proportional to 1 over Reynolds. So if you increase the speed by a factor of 2, your friction will go down by a factor of 2. So a linear dependence. And then we have kind of this line here, which is here indicated for smooth pipes. So essentially a turbulent flow with smooth walls. And all this region up here, this would correspond to rough walls. So walls where you would have a certain roughness, certain type of undulations on the wall, which are large enough to disturb the turbulent flow. Not as we discussed last time when we had very small hills and valleys, but if you really have large roughness in the flow. But the important thing now is to see that essentially this line here, so which is the one that corresponds to the smooth pipe, that this is essentially what we were drawing here, where you had another dependence on the Reynolds number, which is a little bit lower in slope. That's what you see here, and compared to this one. And you also have this jump going from the laminar one up to the turbulent one. And this region, the gray one here, that is this transition region. That's what we also had here, when the flow goes from the laminar state to the turbulent state. So in that sense, the Moody diagram, which you all have seen before, is nothing else than the indication or the quantitative rendering of all the data that was available, but it essentially shows exactly those things that we talked about before. Okay, so that's the Moody diagram, which I wanted to show you. The second aspect that I wanted to talk to you about is actually a little bit more about a couette flow and how one can actually reproduce couette flows both in experiments and simulations. So this one, first, the first part here is experiments that you can do in couette flow. Unfortunately, I don't have a picture here. I should maybe take a picture next time I'm in the lab, but it's just a sketch of an actual experiment that is set up at KTH in our in our lab where we do measurements in quet flow. And you can see how this is actually done in practice. So on the left, you see again the setup of quet with two walls. But on the right here, so figure B, is the real experiment that you can set up. And the basic idea is that you have two axes, one here and one here, and you have a belt, this light gray thing that goes around both of those big cylinders or big axles, and these rotate. So that means that the belt goes on one side in this direction, and on the other side it goes into that direction. And if you put this into an aquarium of water, so you fill these cubes here with water, then of course the belts, they introduce the quet flow motion that we discussed. And then you can do observations of this. So you can put a prism here, and then you can look in with two cameras. The reason why you need to have a prism is that the refraction of the light beams, or of the light beams, essentially is such that the camera here looks at an orthogonal plane, and then everything inside is the same fluid, so that there is no refraction at the interfaces, because otherwise you would not know what the angles are. So you can then do observations on that. So there is a clear way of how you could build such a quet flow experiment. But of course, you can do also simulations of quet flow, and that's what I would like to show you next. I have prepared a few videos that I did myself some years ago, and perhaps the nicest one is perhaps this one, which you find on YouTube. I'll just now try to move that here so that you can see it. So this one, for instance, this is one simulation that we did in quet flow, had a Reynolds number of 350. Don't care or don't worry about the Reynolds number yet, but this is just one specific value. And what we did in this particular simulation is that we started with random noise in the domain. We discretized the Navier-Stokes equations, and what you see here is the mid-plane. So exactly the plane between the two walls that are moving. And now the question is, what happens to the flow if you just started with random noise? If we do that, just play it, you see that this random noise suddenly becomes very small scale turbulence. So all these patterns, or the differences between between white and black, corresponds essentially to different velocities, high speed velocity and low speed velocity. And that's, as we will say later, see also with Ramis in the turbulent part of the course, this are the main features of turbulent flow. So we start essentially having a turbulent distribution. And then if you wait long enough, you see that there is some dynamics here, but then something very interesting happens, which we'll not explain today in detail, but I'm just showing it to you here as kind of a teaser of that there is so many interesting things hidden in fluid mechanics. Well, it actually turns out that suddenly this flow, which was fully turbulent in the beginning, suddenly begins to build these what we call laminar turbulent patterns. So you have parts of the flow which are still turbulent, but then you have other parts which are laminar in between. And this coexistence of laminar and turbulent flow is actually very interesting from a dynamical systems point of view when you start to analyze these flows. So that means this Reynolds number of 350, if you now go back to kind of our diagram here, so this Reynolds number of 350 would be somewhere in this transitional region. So somewhere here would be perhaps 350. Now the question would be, okay, if we now go lower in Reynolds number, so for instance 320, let's see what happens. So for 320, we again start with the same noise that we had before. But then actually it's quite interesting what happens. You see that there is certain parts where turbulence survives a little bit, but if you wait long enough, turbulence actually starts to disappear everywhere. So all these places where we had turbulence are essentially disappearing, except this one here. But if you wait longer, believe me, it will also disappear. And that means that after a certain while, at Reynolds number 320, we actually have recovered a fully laminar flow. That means, now if you go in this diagram, that probably this point here, so the last one, which is fully laminar, would then be 320. Then the last thing that I would like to show you here is if you go to 380, so a bit higher than 350 that we had before. Also there, same thing, we start with noise and we see what happens. So again, we get these kind of streaks and so on. But actually, if you wait, even if you wait longer, there will be none of these laminar turbulent patterns appearing. Everything would just be a fully space-filling turbulent flow. So that means that if you go back to our diagram, maybe this point here corresponds to a Reynolds of, a Reynolds of 380. So that means now, just based on those simulations, but you can also do that in experiments, of course, the range between when you jump from the laminar to the turbulent line, that happens approximately between 320 and 380 in terms of Reynolds. So if you're below 320, you would be laminar. If you're above 380, you would be fully turbulent. In between, it's kind of a little bit difficult to say. Okay, so this I wanted to show you, and of course, if you're interested, you could just go to these links and look at them. Okay, any questions so far? Because then I would continue with the last aspect of quet flow, and that is the application. Application of quet flow. So where and how is quet flow actually important? Well, as we said before, originally this the whole idea of quet flow goes back to Maurice Couette, the French scientist, and in the year 1870, he was tasked with trying to measure the viscosity of different fluids. So he wanted to know, or he wanted to get values for the viscosity of air, of oil, of different fluids, just to understand better the engineering aspects behind these fluids. So he wanted to measure the viscosity. So what does he do? Or how did he try to do that? Well, he built an apparatus which looks like this, that he had a big cylinder, something like this. So a big cylinder, and in this big cylinder, he put a smaller cylinder into the center, something like this. Something like this. And then what he did is he applied a certain speed on the outer cylinder. So rotational speed. Let's say that we used the angular velocity of capital omega for that speed. And then he was measuring the torque that essentially arose from that speed of the outer cylinder on the inner cylinder. So I can say that we have an outer cylinder. The outer cylinder rotates. And one measures the torque on the inner cylinder. And of course, now the idea was that if you measure this torque, you can then somehow determine the wall shear stress tau W that comes from the fluid. And when you know this, this wall shear stress, you can then calculate the viscosity. So that was the reasoning or the idea of Couette. Now let's try to kind of figure that out, how you would actually calculate that. Let's put some geometrical values here. So let's say this whole thing had a height of capital H, perhaps. Let's say that the radius of the big cylinder was capital R. And let's say that the gap between the outer and the inner cylinder is little d. So with this, we essentially have defined the geometry. And if we just do a kind of a blow up of this region, so it would probably look like this. So we have the inner cylinder, we have the outer cylinder. We said that this distance here, this would be R, and the gap width between the inner and the outer would be d. Of course, now the speed here from this omega would be omega times R. Now the idea would be, and that's one of the assumptions that we need to make, namely that we assume that the d is much, much smaller than the R, and that means that we can neglect the effect of curvature. So that means we can essentially assume that these two lines, the inner and the outer cylinders, are parallel to each other. And of course, as soon as they're parallel to each other, then we're back at the situation that we have a Couette flow. So we would expect a velocity profile that would kind of look like this. And of course, that's exactly the Couette profile that we have been talking about. So that's the idea of Couette on how he could have measured the viscosity, and that's why we call this Couette flow. But now let's try to actually calculate the relation between the speed, the omega, and the torque that you measure. Okay, so how would you now measure the torque? Well, the torque essentially is a force times a distance, as you all know, and the force here would be a stress times an area. So that means if we're now just translating all these well-known expressions from mechanics into fluid mechanics, well, the stress would be tau W, which would be acting on this inner wall. This needs to act on an area, so 2 pi times R minus D. That's, if you wish, that's the radius of the inner cylinder. So this is R minus D, and because it's because it's a cylinder, so we need to multiply it with 2 pi to get the circumference of the inner cylinder, and this needs to be multiplied by h, the height, to have the complete surface of the inner cylinder on which the tau W is acting. And then, because this is a torque, we also need to multiply it with the arm, which is R minus D. So I just give names to all of that. It's like this, that this would be the stress. This one here would be the surface area of the inner cylinder, and this here would be the arm of the moment. Okay, Well, now we have all of this. Now we can plug in the values that we know because it's co-ed flow. So we have actually solved the velocity profile. So we can calculate this, which means the stress here, that would be something like mu times omega omega times r divided by 2, and then here you would have d divided by 2, something like that, times 2 pi h, that's the height, times r minus d, and because it's 2 times here, it would actually be r minus d squared. Okay, well, this here is then the formula that you get for the actual torque. And now you can actually identify here interesting things. So for instance, you can see, this one here, that would correspond to kind of a characteristic speed. There is here the d divided by 2. That would correspond to a characteristic length. And then, of course, we have the viscosity here. So you can directly associate the Reynolds number that we have defined earlier to certain parts of the terms here in the expression. And then, of course, there is some other things here as well. But there is a clear dependence on the Reynolds number, in particular when it comes to the speed. So that means now, in the end, we have now found a relation the following way, that mu is actually mu as a function of r, d, omega, and h. So exactly what we wanted to have, or what Couette wanted to have. So in this way, Maurice Couette was then setting up his experiment, and he then put in different fluids, measured different torques, could then get out the viscosity here, and calculate that. So he could then get out, for a measured torque with all the geometrical parameters, you could calculate the viscosity. What he actually did observe at the time, and that's quite interesting also, again, from a historical perspective, he noticed a large increase of the viscosity above some value of the Reynolds number, which could be defined as omega r d divided by the viscosity. So he realized that when he did this setup, and he was increasing the speed, obviously the torque was increasing as well. At first, this was happening in a linear way, because kind of clear, if you increase this, then this one will go up linearly as long as the viscosity is constant, because all the other terms are just geometrical values. But then he realized that at some point this linearity was broken, so that means that suddenly the viscosity became kind of Reynolds or speed dependent. And of course, there was a slight problem, because that doesn't really fit together with the idea of a Newtonian fluid, where actually the viscosity is a constant. It just multiplies the strain rate. Well, of course, now we know what happened. Well, the flow became turbulent. The flow becomes turbulent at a certain Reynolds number, as we have now kind of seen, as we have seen here. When the Reynolds number is above 350 or so, then it becomes turbulent. So the flow becomes turbulent. And of course, that has two consequences. Well, of course, you have fluctuations in it, which then means that the velocity profile is not linear anymore. So that means that the assumption of how to calculate the wall shear stress based on a linear profile is not correct anymore. But also it means that perhaps there was some other modifications in the viscosity that then changed everything. But the main aspect here would be the flow becomes turbulent and the profile is no longer linear. So in a way, we can say that he has already kind of discovered in a quite nice way as well, the fact that there is something happening at some point when you go from laminar to turbulent. So I guess if he had worked more on that, we would not talk about the Reynolds number these days, but perhaps about the Couette number. But I think it remained then up to Couette to Reynolds to actually come up with the final explanation of that. But he was very close in discovering those relations as well. Okay, so this was about the Couette way of measuring viscosity. And actually, it's still done, measuring viscosity is still done in very similar ways these days. So not much has changed really. Okay, now the next topic that I would like to talk briefly about is actually viscosity as a thing. Because we have now talked a lot about viscosity, about how you could measure it, and there's a few aspects that are actually quite interesting to understand about viscosity. So first of all, we have talked about the viscosity, which can be expressed as mu, and then we have also talked about the viscosity that can be expressed as a nu. And of course, we have mentioned that mu here, that is what we call the dynamic viscosity. And the nu here is what we call the kinematic viscosity. And the relation between the two is very simple. I mean that the nu is just the mu divided by the density rho, which then means that the dynamic viscosity has a unit of Pascal times seconds, and the kinematic viscosity has a units of meter square divided by second. So, I mean, at first, these are just two different definitions of the viscosity. Maybe it's interesting at this point also to say that there are some historical units that are used at times. So meter square per seconds can also be called a Stokes. So that's an old unit for viscosity, meter square divided by seconds. So that's exactly Stokes, or also Pascal times second. So the units of mu has a name, and actually this is called Poise from Poiseuille, and actually this corresponds to 10 Poise. So these are slightly older units that are not used anymore. They're certainly not SI units, but it's maybe important to kind of know that these existed. But I guess more important is to understand why these different ways of writing the viscosity actually exist and what their basic meaning is. Well, the dynamic viscosity, the mu here, that's essentially, if we just talk about viscosity, this is the viscosity one talks about. That is the viscosity that directly relates to forces. And that's why it's also called the dynamic viscosity, because it is really related to the force that can be, or the stress that comes from the fluid. So if we just go back to the definition that we had in the beginning, I'm trying to find it. Yeah, here, for instance, so the wall shear stress, that is mu times the gradient, or mu times the strain rate. And so that really relates to the force. That's why it's also the dynamic viscosity. Dynamics, if you recall from your mechanics courses, dynamics is the area of mechanics where forces are relevant. On the other hand, the kinematic viscosity, also there you can think back of the definition of what actually kinematics is in mechanics. Kinematics is the area where you look at where you look at velocities and how motion is happening. And that means that the kinematic viscosity is not directly related to the forces, but rather to the motion. And also this we can kind of illustrate here quite nicely on just the Navier-Stokes equations that we have here. So here we have the equations for the velocity, so for the motion, and that is the equations where the nu is appearing. So it's not directly a force because the density we have kind of multiplied out. It's the nu that relates to velocities, to motion. So that's why you have these two definitions. Another thing that is important when talking about viscosity is actually to have an idea of how big they are. What are values, typical values of the viscosity? And of course, the two fluids that we mainly look at or work with is water and air. Water being a fluid or a liquid, sorry, and air being a gas. And if we just look at the viscosity, the dynamic viscosity of them, mu is approximately 10 to the minus 3 kilograms per meter and second for the dynamic viscosity, and air we have the corresponding value of 1.8 times 10 to the minus 5 kilograms per meter and second. And of course, these numbers also make sense. I guess all of you would have said that the viscosity of air is much lower than for water. I mean, it's much easier to swim in water or to accelerate in water, let's say, swimming in water than it is in air. So I guess this makes sense. But actually it becomes interesting if you then look at the values of nu for, again, both fluids. So nu in water is approximately 10 to the minus 6 meters per square divided by second. And for air, it's this 1.5 times 10 to the minus 5 meters square divided by second. And of course, now you see something that is perhaps a little bit unexpected. Namely, you see that the viscosity, now I'm talking about the kinematic viscosity of air and the kinematic viscosity of water are such that actually the viscosity of air is larger than the one of water. Of course, this is only for the kinematics because you have multiplied the density in, and because the density is also very different, that's why you see this difference. But it's kind of just important to keep in mind that the actual viscosity, what we kind of feel, that would be the dynamic viscosity, because that's the one that relates to forces. Okay. The last thing I would like to talk about when it comes to viscosity is one last aspect. That is an interesting question of how does the viscosity actually change as a function of temperature and maybe also as a function of pressure. Also, that is maybe, it's kind of an interesting thing. Does the viscosity actually increase with temperature or does it decrease? But this we will talk more about after the break. For now, we stop for 15 minutes and we continue at 15:15.